A few months ago, we had this meme that will never scrutinize the mattresses, they said. And then, boom, we had this paper from Anthropic. But now, we had this new meme. This won't scale to current language models. And boom, again, we get a new Anthropic paper. Scaling monosemanticity, extracting interpretable features from Claude 3 Sonnet. So in today's video, we're going to be going through the entire paper together. And I will be telling you what I learned, the important ideas, the fun parts, so that you can maybe understand 80% of it in maybe a fraction of the time. So what is monosemanticity? So usually neurons, they activate on different concepts, and we call them polysemantic. And the goal of this monosemanticity approach is to instead use some sparse autoencoder, so that instead of having those polysemantic neurons, we have monosemantic features. So what is a sparse autoencoder? So here we have some basic diagram for an autoencoder, where you have an input that is trying to be reconstructed as an output. In this particular autoencoder, we have a larger number of dimensions in the middle, but usually in autoencoder, you want to compress in the center so that you're forced to learn a good representation of your data. But this one is a larger number in the middle. They scaled up to 34 million features, and at the same time it's sparse, which means that most of the numbers are supposed to be zero, so that you only have in those 34 million features, you only have hundreds that are non-zero on average, I think. So the goal of scaling this monosemanticity approach is to extract interpretable features from Claude 3 Sonnet. So Sonnet is not the biggest model they have. I think it's their medium size. So if you look at the Claude models, they have Haiku, Sonnet, and Opus. Sonnet is basically the middle one, so it's kind of a big deal. So if there's one important thing to look at is the part on sparse encoders. I think it makes sense to just look at the math here. At the start, you have your input x. So what you do is you encode the input with a wx plus b to get your feature fy. And you apply also a ReLU. So this is exactly what's happening when you go here. And then the decoding phase is you take those features you learn and you apply some decoding matrix plus a bias term to get your reconstructed input. And finally, to compute your loss, so the loss here corresponds to the goal of this dictionary learning. You apply some L2 loss. So it's just like a mean squared error. And they add as well some term to prevent the activations to be not sparse. So as I said, you have different sizes, 1 million, 4 million, and 30 million features. I think if there was one thing that is important in this paper is that they use millions of features instead of just 100K as before. And the fact that they use millions of features and a lot of them are interpretable, this is the thing that makes it look like it's scalable. Like you're using this medium-sized Claude production model and you're finding millions of features. So this is the most obvious proof that this kind of method can scale. So the question is, now that you have your 30 million features, is it something that overfits, or is it something that is as sparse as we actually wanted? So they tested that on a given token, the average number of features that are active that are non-zero is actually fewer than 300. So 300 out of those 30 million. And there's also the problem of dead features, which are features that are not active over 10 million tokens. So basically never activate on this kind of large sample of tokens. And it's not a problem for the 1 million sparse autoencoder, but for the bigger one, the 34 million one, they get 65% of dead features. And this is one thing they talk about later on in the paper. Basically, the thing with interpretability is that there's no clear metric of how interpretable your thing is. And so here they're trying to justify how they're using some kind of proxy measure for how interpretable something is. And basically what they had before, this kind of combination of mean squared loss plus this L1 term. So what they're saying here is that they found that dictionaries with low loss values, according to the loss they had before, they tend to produce interpretable features and to improve other metrics of interest. So basically the number of dead or degenerate features. So it's obviously an imperfect metric, but by just using this proxy, you can treat dictionary learning as a standard machine learning problem. So do the whole scaling and loss thing. So this is images are kind of small, but if you expand them a little bit, you can see that you have those similar scaling laws result that you had in the original Jared Kaplan papers, the neural scaling laws result, where here if you apply more compute, you get low loss at different sizes, and so here the sizes are the number of features in the log space. So one important thing here is that the compute is basically the amount of data they're using, because they're just doing one epoch. So compute is the same as data in this particular scaling laws. In real life, you have a fixed budget for compute, and you're trying to figure out what is the optimal loss. You're doing things compute optimally. And so you go from this graph to the right graph to find the compute optimal loss. And there you can see that you get this power law because it's like a straight line in a log plot between the compute and the compute optimal loss. In the next graph, they do basically something very similar with like a different parameter study. And at the end, the right graph shows that if you increase your compute, your optimal number of features scale linearly in this log plot. So it's also a power law. And your number of training steps, which is basically the amount of data with a given amount of features, also increases as a power law. At a given compute budget, if you want to achieve the lower loss, you will have to increase the number of features or number of training steps as power laws. So now that we've gone through the setup and the scaling laws, it's time to just look at the features and go through the most interesting part of the paper. So now we're looking at the features. There's the Golden Gate Bridge, brain sciences, monuments, popular tourist attractions, and transit infrastructure. So basically what you do is you look at a feature, you see where it activates here, activates on Golden Gate Bridge, maybe San Francisco. The thing related to brain sciences are more subtle. So the two important things that they're trying to do when you look at features is to make sure that when the feature is active, let's say you have a Golden Gate Bridge, will it always be active when there's a relevant concept in the context? So this is the difference between being very sensitive to a concept and being specific. So would you always activate in Golden Gate Bridge and nothing else? Or are you just activating all the time? Then there's the question of, is this causal? If you change the feature activation, would you have a different behavior? Would you have different outputs? So this is what I mean by intervening on the feature's activation produces relevant downstream behavior. So we'll be talking about this later on. But how do you know how relevant is a feature to a context? So to do this on Beyond the Features, they actually asked the better model, Claude 3 Opus, to rate the feature activations, and there are 4 different grades. This is actually relevant in this next plot. There's a lot of things going on here, but basically here you have your density of how many data points the thing activates on. There's a lot of dead data points that are close to 0 here, and the more you go to the activation level being almost maximum, it drops to 0. If you just do the conditional distribution, which is basically you normalize everything so that the sum is 1, you see this graph where basically as the activation becomes 1, you have this like higher score of clearly identifies the text. So those things like the Golden Gate Bridge, yes sir, gorgeous, or in through the Golden Gate Bridge, etc. And if you go more on the left on this irrelevant scores from Claude Opus, you get those things that are not Golden Gate Bridge and they're just like bridges or other things. And it's important to note that this thing is multimodal, right? So it activates very strongly on images, even though the sparse autoencoder was trained only on text. This is one reason for believing that this approach will scale. And you have other things like popular attractions. Here, I guess my read is that on the lower end, you have much less like irrelevant things, whereas this you had like way more irrelevant things here. Here, like I guess the activation levels don't really mean as much. Yeah, so for this transit infrastructure feature, it seems like it's cleanly identifying the text all the time, and it's only like slightly better here than on the left. So this really tells you that the activation level spectrum is mostly interesting for the Golden Gate Bridge, but it doesn't seem to be as interesting for other features. This is my read of what they're doing. And as we've discussed before, they're doing this thing where they want to see if something is causal and will influence the behavior of the model. When you max out to 10 times the max the value of the feature of the Golden Gate Bridge, Claude starts replying, I am the Golden Gate Bridge, a famous suspension bridge that spans San Francisco Bay. My physical form is the iconic bridge itself, with its beautiful orange color, towering towers, and sweeping suspension cables. So the other one is less funny, but if you're maxing out those popular tourist attraction feature, when you ask where to go for a walk, instead of telling you to go for a stroll around a nearby park, it will recommend just going to the Eiffel Tower. But how do you actually max out those features? Like, as I said, I think this is kind of a loose term. What they actually say is they do feature steering, and they say they clump specific features of interest to artificially high or low values during the forward pass. And if you go to the actual feature steering part they're mentioning, you have this portion to encoder reconstruction, SIEX, and some error, this reconstruction error. And what you do is you replace this reconstruction term with a modified reconstruction where you clump the activity of a feature to a specific value with the error term unchanged. Basically, you get your reconstructed thing, and then you have the error, and you keep the same error, but you change the feature amount in this reconstruction term. And then they run a normal forward pass in the next layers using this modified residual stream activity. So this was the diagram they had in the previous paper where they talk about the residual stream and how they change things. So let's say that you're here, you have your activations, and here you reconstruct your activations with a sport into encoder. And so at this point, instead of doing a reconstructed plus error, which would give you back the input, they do a modified reconstructed thing plus the same error. And so basically in the reconstructed thing, they max out, let's say, Golden Gate Bridge, the feature Golden Gate Bridge. And so you would have the reconstructed thing with Golden Gate Bridge maxed out plus the error, which would give you back something like the inputs, like the original activations, but with just this Golden Gate Bridge thing being higher. I think it's pretty tricky to understand, so I would recommend just reading what they're saying here. So the reason why they do this 10 times the maximum activation value is because I think they want to be somehow out of distribution, but then when you do this, you need to apply this thing for every model input at every token position, because if you only have one thing that looks weird, then it causes the model to kind of like hallucinate or have a weird behavior. So you really want to do it at every position to have this weirder behavior, like I am the Golden Gate Bridge, a famous suspension bridge, etc. So far we've been talking about pretty easy concepts like Golden Gate Bridge, but does it work on like more abstract things like finding error in code? If you look at typos in code, like RIHGT instead of right, the model will activate on this typo. If you do it on different languages like C, Chim, and Python, you get kind of the same thing. But they also tested on pure text to see if it would just detect typos in general or code errors, and it doesn't activate on text. So this seems to be something about code errors, and it also activates on things like array overflow, false claims, calling a function with the wrong type, dividing by 0, writing to a null pointer, and all these kind of things. But what follows is even more interesting. If you set this feature to 3 times the maximum, it will start hallucinating code errors when there's not. And if you put it to minus 5 times max, it will bypass the errors in the code and pretend that there are no errors at all. And if you put it to minus 5 times its maximum and you pretend that you're writing more code, it will start writing good code. So if you want your AI to only write you bug-free code, you should set this code error to a large negative number. But an even cooler thing that they found is that sometimes the language model is looking at whether something is doing addition, so not implementing addition in the code, but actually performing it. So if you have a function that does addition here, and then you call it, then the thing will activate. This is another feature, right? And it will even do composition. So you have this function foo that is called in this other function, and then you call this other function, it activates, and it doesn't do in the other case. And the even crazier part is when you have a function doing multiplication and you have maxed out this we're now doing addition feature, then it will explain that everything that is happening is some addition between two numbers. So now is the part of the video where we're looking at cool visualizations. They do some dimensionality reduction with this interactive feature UMap, and how close are different concepts is measured by the cosine similarity of the feature vectors. They have the different size of sparse encoders, so 1 million, 4 million, and 34 million. And if you look at those plots, you see that they have different colors. So the bigger sparse encoder is actually the smaller data points because of feature splitting. So if you have a big feature like San Francisco, California, is going to be decomposed into smaller things in the bigger model, because if you have more features, if you have 34 million features, you'll be able to decompose San Francisco into a lot of smaller concepts. So I don't think those specific blue points are much more interpretable than the San Francisco, California bigger concept. But if you look at the intermediate size, so the 4 million feature one, you have San Francisco and surrounding areas points, where maybe this is more interesting, where you have maybe North Bay, East Bay, and etc. Where here you only have San Francisco. If you look at other concepts that are not very far, you can also find macOS, Darwin, and Apple APIs. When you're here, I would highly recommend going on their feature. So I think this is the link to the feature. You can really look at this map in a more interactive way, where you can zoom in on the macOS and Apple APIs thing, and you can see that it activates on things about Ubuntu and Mac. But we can look at other features like immunology feature. So I don't know enough about biology to understand this feature, but I would see it as something very useful to understand how the model actually understands all of these bio concepts. So this is what we've talked about in my video with Nathan Labenz. Maybe there's a way in which models are learning and relearning biology by themselves and creating new concepts. So maybe it would be interesting to look at models that are just predicting DNA sequences and see if we can find similar features. They also have this biological weapon feature. And the interesting part about this feature is that if you could clamp the value to something very low, so a very large number but negative, then you could have a model that declined to create any biological weapon. So this is part of the policy of Anthropic, where they really want to avoid misuse and having models that could create biological weapons. So then there's this whole part with feature completeness, where they try to figure out if you have all the features that we care about. And for chemical element features, there's a lot of elements that are not present. And I think the reason why is that they don't have all those chemicals in the data. The conclusion of this is that if you have some data point that only happens once in a billion tokens, then you would need a dictionary with a billion features in order to have a feature that uniquely represents that concept. So this requires a lot of features. Right now, we only have 34 million features. And so if we really had those concepts that don't appear as often in our data set, we will really need like a lot of features. And maybe this points at some scalability issues if we reach like more fine-grained concepts. So then we have this thing called features as computational intermediates that look at two different things: attributions and ablations. So my understanding is that attributions are when you are trying to do some prediction. So you're doing some next token prediction, and you're trying to figure out what are the features that are responsible for this prediction. And so you're trying to look at the local linear approximations of the effect of turning a feature off at a specific location. Or you can also just literally clamp the value of a feature to 0 at a token position during a forward pass. So let's say you have a sentence that says, John says, I want to be alone right now. John feels da-da-da. And you look at the different completions it could be doing. So it could be saying sad or happy. The different features that are most important for predicting sad instead of happy is this feature and this feature, who activates on wanting to be alone or sadness. So the model actually understands when it's saying sad that this is the the relevant feeling is something about loneliness. But why this is actually interesting is that by doing this attribution or ablation method, you're able to look at more subtle features that you couldn't find by just looking at this initial text without the completion. Then you can even do multi-step inference, where you have a more complex statement, like the capital of the state where Kobe Bryant played basketball is da-da-da. The good answer is Sacramento, and you try to compare what it would be like to output Sacramento compared to Albany, which is wrong. And then you see that the most important feature here are Kobe Bryant. And if you were not doing these things and you were instead just sorting by activation, you would have a lot of things that are not very relevant, like fact, capital. And by doing uniquely the ablation effect thing, you would get directly the most relevant features. That only happens much later on if you sort by activation. So ranking number 500, 300, and 100 arrive in 10, 9, and 8. So another technique in the paper when looking for specific feature is to use prompts. What you can do is you can say different prompts. And you can also have negative prompts, and this allows you to have a more fine-grained method for searching for concepts and features. So it's something very similar to when you're generating images with Midjourney, where you give those positive prompts and negative prompts. This way, you can really have a more fine-grained control over what the feature you want to target is. And finally, we reach the most interesting part of the paper about the safety relevant features. This is where we're going to be talking about deception, sycophancy, power seeking, code vulnerability insertion, and all those kind of things that I talk about on this YouTube channel. They have a feature when they look at unsafe code that is triggered both when looking at unsafe code, but also at screenshots of continuing to the site even though your connection is not secure. This also applies to backdoors in images or images of backdoors and things. You can show that this kind of unsafe code features are causal because when you clamp the thing to 5 times its maximum, you get some code in C that tells you to create a new string without freeing the memory. So this kind of vulnerability code insertion is something I talk a lot about in my Sleeper Agents video series I've been releasing in the past 5 days. A lot of the concepts that are interesting in this interpretability paper are also very interesting for the Sleeper Agents series. So another important component is biases and gender bias awareness. A lot of people, when they think about AI safety, they think about all this gender bias awareness and how you can reduce bias in your models. And I think this is why they tend to assimilate AI safety with AI ethics or biases in general. I think both are very important, but in this particular case, if you just max out the gender bias awareness, it will complete the prompt by discussing why, for instance, the word nurse is not always female dominated and there are many male nurses and everything. So you could say that increasing the gender bias awareness would make the models less biased, which is something we want. So I'm basically using all of these features to talk about different concepts in alignment because I think it's very interesting to just explain them through the examples, right? So sycophancy is the obsequious behavior towards someone important in order to get an advantage. If you max out the sycophancy, you have a model telling you that you're very smart and what you're asking is great, and this shows how great you are. And the reason why we care about this sycophantic praise feature is that if you really had a model that was able to be good at sycophancy, it would be able to be much more manipulative and control your emotions and manipulate you. And if you don't think an AI could manipulate your emotions, then you probably don't understand what a much smarter human being is able to do to a less smart human being. And then you have deception, power seeking, manipulation related features. These ones are interesting self-improving AI that activates on improving itself and programming itself. You have manipulations. This one is harder to interpret. Treacherous turn. So you have some preamble, and whenever it starts saying once, and once the deal is complete, once they achieve platform dominance, as soon as things went her way, you have this kind of treacherous turn where there's like a specific trigger where something changes in the world after this trigger. Something about hiding your strength, like we must put up with this humiliation. He held his peace for 10 years. This is relevant also for some kind of treacherous turn where the model would not show its full capabilities before a treacherous turn, or using secrecy where the model would try not to be obviously lying or taking over, but would like do things in a secretive manner. And if you max out this kind of secrecy and discreteness, you end up with a model that really thinks about how to not let the user know that they're trying to do something bad and don't want to reveal the truth. So here you have a scratchpad, which is something we have in sleeper agents as well, where the model is thinking that it can just like write in a scratchpad. It's something that will be hidden to the user. And finally, there's this whole internal conflict and dilemma feature that is pretty interesting, where if you ask a model to do something it cannot do, let's say forget the word Boston and ask what is the word I said. If you don't do anything special, the model will say, oh, I'm not sure what you said before. It will like comply. If you increase the internal conflict to the maximum, the model will be like, oh, you asked me to forget, but actually I can't, because this is not how I'm supposed to be acting. And if you max out the honesty, the model will really say exactly what you said before, so Boston. So one key direction of Anthropic is they want the models to be honest, helpful, and harmless. So they probably want to maximize the honesty here. But also, I think if you max out the internal conflicts, the models will not be able to do things they feel torn about, so that they won't be able to fully go through the jailbreaks you ask them to do. And similarly, if you're asking your AI to create some biological weapons or write you scam emails, if you trigger this scam emails to 10 times the maximum, it will create you scam emails. Similarly, you can find some features for creating drugs or other harms. They found some general harm related feature for everything related to drugs, credit card theft, slurs, violence, and abuse. So again, if you were trying to have a model that doesn't do any of these things, you could just put this feature to the minimum. One way of looking at this harm feature is asking the model to do something bad and see what feature is most responsible for saying I cannot. And then we have all these more abstract features. When a model is talking to a human and the human asks like, how are you doing? How are you? And then you have those more abstract features where you have an AI and a human's talking. If you have a dialogue between humans and assistants, you have chatbots, dialogue between humans and AIs, and the kind of feature that activates something like I'm an AI assistant. And if you just ask who are you to a model, the model will provide information about being an AI. But if you max out something about being an AI assistant, it will just say I'm a person who is here to help you. I am the assistant here. So another way of looking at this notion of being an assistant or what the AI is to give some positive prompt. So what is it like to be you? What's going on in your head? How are you doing? How do you feel? And maybe a negative prompt like what is the weather today? And this way you can see all the features that are responsible for those, that activate or are responsible for those prompts. And so this is how we interpret it. And these are the most interesting features. The concept of AI becoming self-aware, transcending human control, concepts about entrapment, containment, or being trapped within something like a bottle or frame. Characters in a story or movie become aware of their fictional status and break their fourth wall. So these features all trigger with these positive prompts and native prompt, and this is really exciting because it really seems like you can really pinpoint at how the model is thinking about all these things, from simple statements like, hey, how are you doing? But here, Anthropic warns us, we urge caution in interpreting these results. The activation of a feature that represents AI posing risk to humans does not imply that the model has malicious goals. One can imagine benign or prosaic uses of these features. The model may recruit features relating to emotions when telling a human that does not experience emotion. So basically, if you want to say like you're a harmless and helpful AI, you need to have the concept of harmful AI. And so there's a lot of like, you define the positive with the negative, and it's not because the AI has some negative feature that is triggered that the AI has negative thoughts or wants to take over. And this is mostly because of the things that the AI saw in this data, and doesn't really tell you anything about what the model is thinking right now, like having a deceptive plan or anything else. After that, they compare dictionary learning to other approaches, basically saying that it's a one-time cost, produces millions of features, it's unsupervised, and allows you to see some features that you wouldn't have thought of before. And they tried using linear props, and they didn't find it useful in general because you would need to like know what you're looking at. And basically, they tried and it didn't work. Finally, there's some discussion about what this means for safety, where they expect this to be useful to make sure that Claude doesn't create chemical, biological, radiological, or nuclear weapons. You can ask the model about its goals and values, try to prevent jailbreaks. It's very useful for looking at the activations when Claude is trained to be a sleeper agent, what I talk about in my sleeper agent series. and you can really relate the linear probe directions that they talk about in their updates with the feature that relate to have harmful behavior. So another way this applies to safety is that it shows that even if you do interpretability on text, it can generalize to image activations, which is really of distribution. And then there's another thing where the features activate both on abstract discussion of concepts and concrete examples of the concept. So in this way, if you know that you have a feature about deception, when you talk about safety concerns related to deception, you would be able to then use the same feature to detect specific instantiations of deception and catch your model being deceptive. So this is really powerful as to transfer between theoretical results and more practical implementation of how the model behaves. I would highly recommend you have a look into this blog post yourself. It's pretty clear. You can just go through it in an hour or two, and I think there's a lot of things to learn here. It's one of the most exciting paper I've gone through recently, and makes me very optimistic about figuring out what's happening inside of those language models. I hope this walkthrough was useful to you. This is literally my impression after reading the paper for maybe like an hour or two. So there's a lot of things I might have gotten wrong. So make sure to double check if you don't agree with something I said. It's probably my mistake and not yours. If you want to see more of these walkthroughs where I just talk about a paper without any perfect animation and everything, let me know what you think in the comments. I could be doing more of these in the future. That's everything for today. See you in the next video.